Very good morning, my dear students. In the last class, we have started module 7 and we discussed the importance of QPSK, Quadrature Phase Shift Keying or Binary Phase Shift Keying. So if you observe this slide, you can see that. See, please observe this slide. If you observe this, you can say that the QPSK system is bandwidth efficient system compared to BPSK because it transmits 2 bits per symbol at a time, and at the same time it will reduce the bandwidth. So almost all the bandwidth needed to transmit the QPSK signal is FB, and you are transmitting 2 bits. So that's why it is called as 4-array PSK, because here we have 4 possible combinations of phase changes. Okay, here dbit means that die bits, so 2 bits are simultaneously transmitted, so it is called as. So in QPSK we have like 2 number of bits are grouped per symbol and that will be transmitted. So because 2 number of bits are transmitted, we will have 4 possible combinations of phase changes. So that's why so we can assume that there are 4 symbols present at the respective locations of phase changes. And similarly, so what is the bandwidth? Its bandwidth is FB and it is almost all reduced to half that of BPSK. So because BPSK needs 2 FB bandwidth and then our system needs FB bandwidth. So bandwidth is reduced to half and 2 bits are, so double the amount of bits are transmitted over BPSK. So 2 bits are transmitted here. So 4 possible combinations of signals are available. So using those 4 possible combinations, and already I said you that we can interpret QPSK as 2 independent BPSK systems. Okay, you can interpret QPSK as 2. You can interpret BPSK. You can take 2 BPSK systems, one in the in-phase channel and other in the quadrature channel, and you can construct our QPSK system. So QPSK system can be considered as a combination of 2 BPSK systems, one in the in channel and other in the quadrature channel. So if you observe the constellation diagram, already I told you it consists of two carriers. One is in-phase component, which is due to the even bit sequence, and phi naught of t is due to, it's also the 1-bit energy carrier, but it is due to quadrature carrier, and that is due to odd sequence. So please observe the QPSK. Here we will have 4 symbols, S1, S2, S3, S4, and these 4 symbols are constructed based on the 2 input bits. So what are the input data bits? So you can consider it as either 0 or 1. So because 2 bits are grouped, 4 possible combinations can be 0, 0, 0, 1, 1, 0 and 1, 1. So for the binary data 0, we are assuming the voltage level as -1. And for the binary data 1, we are considering the magnitude as +1. So mean that you are converting like unipolar to bipolar. And here you can observe the carrier phase. So carrier phase is equal to pi by 4, 3 pi by 4, 5 pi by 4 and 7 pi by 4. Please observe here you will have a phase shift of 2 pi by m. What is m? M is 4 in the case of QPSK. So upon replacing m as 4, you can get it as pi by 2. So each phase shift is, each symbol is deferred by a phase of pi by 2. So if you take any 2 successive symbols, the phase difference is pi by 2. Okay, so this is about the QPSK constellation diagram. So already we discussed the generation block diagram. Initially unipolar signal is converted into B of t, and using demultiplexer it is split into 2 sequences. One is even and other is odd bit sequence. Here even bit sequence is multiplied by root PSTS into the energy carrier, in-phase energy carrier, because you have cos 2 pi FCT here, and the output due to the multiplier is SC of t. And what is S naught of t? B naught of t into root PSTS into phi naught of t, where phi naught of t is the quadrature carrier. So because you represented sign here, so it is a quadrature carrier, and B naught of t is the odd sequence. Okay, the sum of these two gives you our QPSK signal. Sum of these two components gives you the QPSK signal. So already I told you the even sequence will, the magnitude of even sequence will change only at even intervals. That is 2, 4, 6, 8, 10, 12 like that. So, and our odd sequence will change its magnitude only at odd intervals. So our demultiplexer will split B of t sequence into B naught of t and B of t. So because our QPSK groups two bits per symbol, one bit is due to odd sequence and other bit is due to even sequence. And next is odd, next one is even sequence. Like that it is grouped. So B of t you can demultiplex into B naught of t and B of t. If you multiplex B naught of t and B of t at the receiver, you can extract B of t. Okay, let us go to the next slide. See here you can observe a level shifter due to both I channel and Q channel. It is raised by magnitude of root PSTS. So SC of t will be B of t into the product of all the factors gives you your SC of t. And similarly, please observe S naught of t. So S naught of t is a product of B naught of t root PSTS root 2 by TS sine 2 pi FCT. where phi naught of t is the quadrature carrier and phi of t is in phase carrier. So already I told you QPSK signal is a sum of SC of t and S naught of t, where SC of t is B of t into root 2ps into cos 2 pi FCT, where cos 2 pi FCT is in phase carrier and sin 2 pi FCT is quadrature carrier. So the sum of the in phase component output and quadrature phase component output, that is SC of t and S naught of t, gives you QPSK signal. So finally you got the signal in the form of BE of t root 2ps cos 2 pi FCT plus B naught of t root 2ps sin 2 pi FCT. Okay. Next. And even we discussed the same in the last class. And here I told you that our signal space, using the signal space representation, also called as the constellation diagram, you can calculate the Euclidean distance. So Euclidean distance is the distance between two successive symbols. So you can take the distance between S1, S2 or S2, S3 or S3, S4 or S4, S1. Okay. So, but what is the phase difference between any two successive symbols? It is 90 degrees. So that's why using Pythagoras theorem, you can calculate the distance between S1, S2 as AB. Okay, so you can obtain using Pythagoras theorem as root of OB. Distance is root PSTS. And similarly, already you know the magnitude of phi of t is root PSTS and phi naught of t symbol S2 is also same, that is root PSTS. So that's why using Pythagoras theorem, you can obtain it as root 2 ES, which is equals to root 2 PSTS, where you can replace TS as 2 TB. So in QPSK, you can, so please replace TS as 2 TB. If you replace, you can get it as a root PS into TB. So which is 2 root EB. So we can say that the Euclidean distance of QPSK is same as that of BPSK. So that's why the probability of error performance of QPSK is similar to that of BPSK, because both the Euclidean distances are same. Okay. So what is the Euclidean distance of QPSK? 2 root EB, where EB is PS into TB. Okay. Next, please observe the QPSK waveforms. I think from this onwards we should start in the today's session. So please observe the constellation diagram. Here already I told you the first symbol is both positive. So x-axis is phi of t and y-axis is phi naught of t. So what is the magnitude of symbol S1? 1, 1. Similar symbol S2 is -1, 1. Symbol S3 is -1, -1. And symbol S4 is 1, -1. If you take 1, 1, so please observe the in phase waveform is the first waveform, and quadrature waveform is second one, and third is QPSK. Okay, so what is S1? S1 is 1, 1. Please observe 1, 1. What is the first one? In phase component. So it is cos omega ct. So cos will have 90 degrees phase shift as sine. So we have 90 degrees phase shift here. Next, quadrature carrier is sinusoidal component. Because its magnitude is 1 and it is sinusoidal, direct sinusoidal you will represent here. And here it is, in phase is cos omega ct. So that's why you have 90 degrees phase shift. Now, second one is 0, 0. So where is 0, 0? That is, the magnitudes are -1 and -1. Okay. So mean that minus cos omega ct minus sin omega ct. So you should represent minus cos omega ct and minus sin omega ct. This is cos, and minus will be inverted form of 1. So you will get inverted form of 1 here. So minus cos omega ct will be total. So this is the inverse of cos omega ct you will get. So that's why we represented like this. Next, 0, this is for quadrature carrier. So minus sign. So sign you will get represent like this, and minus sign will be inverted form of sinusoidal. Next is 0, 1. So 0, what is in phase carrier? Cos. So that is plus cos omega ct. Okay. So that's why we represented normal cos omega ct. Okay, because there is no phase change when compared to the earlier data bit. Next data bit is 1. So 0, 1. Please observe 0, 1. Next 1. For 1, what is the magnitude? That is sin omega ct. So that directly we represented sin omega ct. Okay. Next magnitudes are 1, 0. 1 mean cos omega ct. 0 mean sin omega ct. So cos omega ct directly we represented. 0 mean magnitude of -1. So minus sign. So inverted sinusoidal we represent here. Next, the combination of these two signals gives our QPSK signal. Already I told you QPSK signal is a combination of in-phase carrier output and quadrature carrier output. So here you can observe the same using representation. See, for example, I will tell you QPSK signal. Take 1, 1. Here first LSB bit represents the Q phase, MSB bit represents I phase. Okay, 1, 1. First one represents cos omega ct. Second one is quadrature, so sine. So both have 1 magnitude. So plus cos omega ct plus sin omega ct. Now take root 2 as common from this. So you will get 1 by root 2 into cos omega ct plus 1 by root 2 into sin omega ct. So you can represent 1 by root 2 as cos 45 degrees. And here 1 by root 2 as sin 45. Okay. So you can represent it as sin a plus b. So that's why sin omega t plus pi by 4. B is how much? 1 by root 2 cos. So you can write it as cos 45, 1 by root 2, or sin 45 is also 1 by root 2. So that's why you can get sin a plus b. Okay. So why root 2? Because already we took root 2 as common from this. Then only you can represent in this form sin of a plus b. Similarly, minus cos omega ct plus sin omega t. So here also you took root 2 as common. So everywhere while evaluation, take root 2 as common. If you take root 2 as common, you will get in the form of like cos a cos b plus sin a sin b, or in some expression you will get. Okay, so finally you will get all the magnitudes as sin omega ct plus pi by 4. Similarly, sin omega t plus 3 pi by 4 plus pi by 4 plus 7 pi by 4. The intention here is to show that the corresponding phase of S1 is how much? 45 degrees with respect to x-axis. Next, S2 is 3 pi by 4 like angle with respect to x-axis. And next, third one, that is 0, 0. Symbol 3, the angle made is 5 pi by 4. Similarly, S4, the angle made is 7 pi by 4, like this. Okay, so this is about the QPSK waveform. So the thing that you should remember is it is a combination of I phase and Q phase. Okay, so I phase and Q phase. So the sum of these two waveforms gives you our QPSK. So first, so if you take a S1, 1 represents, LSB bit represents the quadrature carrier and MSB bits represents the in-phase carrier. Okay, this is how you can get the QPSK waveforms. So this is a combination of IQ combination. So in phase, quadrature phase. In phase is cos omega ct and quadrature phase is sin omega ct. So you can observe get the waveforms using the constellation diagram. Okay, now let us move to the next slide. So where you can see the coherent detection. So QPSK is almost all the working principle is same as that of BPSK. I told you that it is a combination of two BPSK signals. Okay, so because it is a combination of two BPSK signals, almost all our detection principle is same to that of BPSK. So here also only coherent detection exists, and here also the non-coherent version is the differential QPSK. So actually that is not in your syllabus, but you should know. That's why we are like we don't discuss in detail. So coming to the coherent detection, I told you in coherent detection we'll make use of synchronous carrier. Synchronous carrier. Okay, so almost all the working principle is similar to BPSK, but in QPSK you will use everything like it because it is a 4-array PSK. Please observe the block diagram here. Please observe the block diagram of coherent detection of QPSK. Okay, here the input to the receiver is noisy band limited PSK signal. I think you know the general form of QPSK signal. What is the general form? It is a sum of SU of t plus S naught of t. Okay, so similar to the BPSK coherent detection, here also we will use almost all the same principle, but here you will have two correlators because at the transmitter you used two modulators. I channel and Q channel modulators are used. That's why two correlators are used at the receiver section. Okay, the receiver signal is applied to three sections similar to BPSK. In BPSK, we use a square law device and frequency divided by 2. Please observe carefully. In BPSK, you used square law device here, and band pass filter at 2 FC we used, and frequency divider by 2 we used. But here, because it is a 4-array PSK, please raise the magnitude by 4th power, and then you use band pass filter to allow only 4 FC component and frequency divided by 4, so that you will get cos 2 pi FCT as the output as a synchronous carrier from using these three steps. In the case of BPSK, we used three sections, namely square law device, band pass filter and frequency divider by 2 to generate the synchronous carrier. Here also we'll use almost all three sections, similar sections, but with a factor of 4, not with a factor of 2, because quadrature PSK will allow what it will do. It is a 4-array PSK. It groups two symbols. So because it is a 4-array, use the factor by 4 everywhere. So raise the input by 4th power, and similarly band pass frequency be 4 FC and frequency divided by 4. Then what is the generated carrier? Synchronous carrier, that is cos 2 pi FCT. But at the transmitter we are using two channels, two sections we are using, two modulators. One is in phase, which uses in phase carrier, and quadrature phase modulator, which uses quadrature carrier, that is sin omega ct. That's why once we generate the carrier from these three sections, carrier component in phase carrier is directly applied to the in phase carrier. Please observe the circuit. The in phase carrier is directly applied to the multiplier 1, that is correlator 1. Okay, and quadrature phase carrier is applied to the correlator 2, because this is a Q phase channel. So correlator 1 acts as in phase channel and correlator 2 acts as Q phase channel, similar to the transmitter. Okay, so here directly cos 2 pi FCT is applied to the correlator 1, so multiplier 1. And multiplier, what it will do? It will take the product of received signal QPSK signal into cos 2 pi FCT. Both are multiplied and applied to the low pass filter. This low pass filter performs integration. The integrated data, which is a combination of even sequence. Why even sequence? Because you are using in phase carrier in the correlator 1. So it will generate even sequence. That even sequence along with the odd sequence obtained from the correlator 2. Here correlator 1 and correlator 2 both possess multiplier followed by low pass filter. In BPSK we will have only one section, one correlator, but here QPSK is a combination of two BPSK receivers and two BPSK transmitters. So that's why here you are using one correlator in the I channel and other correlator in the Q channel. For correlator 2, multiplier inputs are, one is QPSK signal and other is sin 2 pi FCT. So what will be the multiplier output? Multiplier output is a product of SQPSK of T into sin 2 pi FCT Both are multiplied and fed to the low pass filter. So what this low pass filter will do? Once again it will perform integration. We'll consider the limits as odd limits for the low pass filter, for the correlator 2 low pass filter. For the correlator 1 low pass filter, we'll take the limits for the even intervals, that is from 2k TB to 2k plus 2 TB. Okay, so it will consider for the even sequence, because for example put k is equal to 0, then it is from 0 to 2 TB. K is equal to 1, so 2k TB to 4 TB. Similarly 2, 4 TB to 2 to 4 plus 2, 6 TB. So anyhow, the low pass filter used in the correlator 1 performs integration for the even intervals. That's why it generates even sequence. Similarly, the low pass filter used in the correlator 2 performs integration for odd intervals. So odd intervals are from 2k minus 1 TB to 2k plus 1 TB. 2k minus 1 TB to 2k plus 1 TB. Okay. See, please observe correlator 1 and correlator 2. Both consist of multiplier 1 and multiplier followed by low pass filter. Here multiplier 1 takes the product of received signal and cos 2 pi FCT, that is in phase carrier. And low pass filter performs integration for even intervals. So the output is now, it will be in the form of even sequence, because integration is performed for even intervals and multiplier 1 takes the product of a received signal and cos 2 pi FCT. Okay. Similarly, if you take the correlator 2, multiplier 2 takes the product of QPSK signal and sin 2 pi FCT. The multiplier 2 output is fed to the low pass filter. This low pass filter performs integration for odd intervals. So the low pass filter used in the correlator 2 performs integration for odd intervals. Okay, so that's why you will get the output from the correlator 2 as the odd sequence, because here you will multiply with quadrature carrier and integration is performed for odd intervals. So you will get odd sequence B0 of t into TB into root 2 PS. If you observe the outputs from correlator 1, it is proportional to BE of t. Similarly, if you observe the output of correlator 2, it is proportional to B0 of t. Now both the signals are fed to the multiplexer. What this multiplexer will do? Multiplexer will simultaneously add these two sequences, even bit sequence and odd bit sequence. So that first bit is odd and second bit is even. So here the demultiplexer at the transmitter and multiplexer at the receiver section are used for timing synchronization. So what is the need of demultiplexer at the transmitter? We used demultiplexer at the transmitter to split B of t into BE of t and B naught of t. Okay, so similarly at the receiver, you are using multiplexer to add the two sequences. So that's why demultiplexer at the transmitter and multiplexer at the receiver are used to provide timing synchronization. Okay, now let us move to the next slide. Please, all these points I told you the same points in BPSK. Okay, so first one here, phase lock should, in order to satisfy the phase lock, two criteria our circuit should satisfy. One is frequency or phase synchronization or timing synchronization. Already I told you frequency or phase synchronization is provided by the synchronous carrier. So here we used three sections, namely power raised per 4, frequency divider and bandpass filter. These three sections are used to generate synchronous or coherent carrier. Okay, this synchronous or coherent carrier is used for frequency or phase synchronization. And the timing synchronization is provided by the demultiplexer and multiplexer. Okay, demultiplexer at transmitter and multiplexer at receiver. Now, the in-phase carrier, already I told you, in-phase carrier cos omega ct and incoming QPSK are fed to the multiplier present in correlator 1, which is followed by low pass filter to perform integration. Simultaneously, QPSK signal and quadrature carrier are fed to the multiplier present in correlator 2. This is followed by low pass filter to perform integration. Both the integrated outputs are fed to the multiplexer in order to generate the sequence B of t. This slide gives you the working principle of QPSK receiver. So let us go through the mathematical analysis of correlator 1 present in QPSK. I told you correlator 1 consists of multiplier followed by low pass filter. That low pass filter, I told you, it performs integration for even intervals. And multiplier takes the product of QPSK signal and cos omega ct. So what is the general form of QPSK signal? The general form of QPSK signal is BE of t root 2ps cos 2 pi fct. This is SE of t plus B naught of t root 2ps sin 2 pi fct, which is S naught of t, due to Q channel, and first term is due to I channel. Both are added to generate QPSK. Now, what is the multiplier 1 output? That QPSK signal into in-phase carrier, that is cos omega ct. So that's why we took QPSK multiplied by cos omega ct. So first term consists of cos omega ct. So multiplied by cos omega ct gives you cos square here. And for second term, you will get sin omega ct, cos omega ct. So sin omega ct into cos omega ct. Please see here sin omega ct into cos omega ct you can represent as sin 2 omega ct plus sin a minus b, that is 0 divided by 2. Similarly, cos square you can write it as 1 plus cos 2 omega ct divided by 2. So finally you got some value that is fed to the low pass filter. So low pass filter, already you know that it won't allow the higher frequency components. Here sin 0 is 0, so that's why you can eliminate this term. So sin 2 omega ct and cos 2 omega ct. So our low pass filter did not allow these two terms. Then what is the output for low pass filter? If you observe the output for low pass filter, it is BE of t into only DC term you will get, that is BE of t into root ps divided by 2, because 1 by 2. Only DC term you will get as the output from low pass filter. So you will get BE of t into root ps by 2. b of t into root 2ps divided by 2 వస్తుంది. So if you take inside, so you will get root ps by 2. So what is the low pass filter? What it captures? It will take only b of t root ps by 2. Please take the integration of this value for the limits. What are the limits? Multiplier 1 output is fed to the low pass filter. Okay. Please see here. See, multiplier 1 output is fed to the low pass filter. Low pass filter, what it will do? It performs integration at even time intervals. Even time intervals. So what are the limits? So 2k TB to 2k plus 2 into TB. Okay. So b of t root ps by 2, where b of t root ps by 2 is nothing but the captured data by low pass filter. So take the integration and apply the limits. So here b of t can be either plus 1 or minus 1. Can be either plus 1 or minus 1. So b of t into 2k TB plus 2 TB minus 2k TB. Just we applied the limits here. Because integration dt is t. So apply the limits and you will get b of t into root ps by 2 into into 2 TB. Okay. So take this 2 inside the root. So you will get 4. So divided by 2 you have. So TB into root 2ps into b of t. So finally, what is the output of low pass filter which performs integration for even intervals? It is proportional to b of t. It is proportional to b of t. Now, similarly, let us calculate the analysis part of correlated 2 in QPSK. Please remember this value. L1 is equals to TB into root 2ps into b of t. Okay. Now please observe the mathematical analysis of correlated 2 in QPSK. Already I told you the same correlated 2 will also consist of multiplier followed by low pass filter. But this multiplier, what it will do? It will take the product of QPSK signal and sin omega ct, where sin omega ct is the quadrature carrier. Where sin omega ct is quadrature carrier. Okay. So QPSK signal multiplied by sin omega ct. Please substitute QPSK signal. It is in the form of b of t root 2ps cos 2 pi f ct plus b naught of t root 2ps sin 2 pi f ct. Okay. So multiply with the sin omega ct. What you will get? In the first term you will get cos omega ct into sin omega ct, and the second term you will get sin square omega ct. Okay, please observe the first term. What you did here? Cos A sin B. So you can write it as sin A plus B minus sin A minus B divided by 2. Sin A minus B is 0. Sin 0, that will be 0. Sin A plus B will be 2 omega ct divided by 2. Plus b naught of t root 2ps into 1 plus sin 2 omega ct divided by 2. Now if this whole factor is applied to low pass filter do not allow the higher frequency components. So our sin 2 omega ct, and here you will have one more sin 2 omega ct. Both will be, you can eliminate our low pass filter, eliminate the higher frequency components. So these two components will be eliminated and you will get only the DC component. Here you have 1 by 2. So only the DC component will be allowed by the low pass filter used in the receiver. Okay, so that's why what is the output of low pass filter? What the low pass filter captures? B naught of t into root ps by 2. Now it performs integration. Okay, so if you take the integration for the whole signal, integration of sin will leads to 0 here. So let us calculate the integration only for this term. Okay, what is the term? B naught of t into root ps by 2 dt. So I told you the low pass filter used in the correlated 2 performs integration performs integration for the limits sorry. So what is L2 here? L2 is 2k minus 1 TB to 2k plus 1 TB B naught of t into root PS by 2 dt. So please apply the integration of dt. So it will be t. So apply the limits. That is 2k plus 1 TB minus 2k minus 1 TB. So you will get directly 2 TB. So directly 2 TB. So divided by root 2 you have. Take that root 2 inside the root. So you will get TB into root 2PS into B naught of t. What is the low pass filter output now? Almost all the analysis of correlator 2 is same to that of correlator 1. Okay, so it is proportional to B naught of t with a proportionality factor of TB into root 2PS. Similarly, what is the output of correlator 1? TB into root 2PS into B of t we obtained. Now these both signals, both these components, now both the outputs from the correlator 1 and correlator 2. Correlator 1 gives you B of t because it is proportional to B of t, and correlator 2 is proportional to B naught of t. So both are forwarded to the multiplexer. So what the multiplexer will do? The multiplexer will group the two sequences B of t and B naught of t without any disturbance. Without any disturbance, it will reconstruct our B of t sequence. What this multiplexer will do? Multiplexer will just, it will group the B of t sequence and B naught of t sequence. So without any disturbance to reconstruct the original sequence B of t. So here I told you this point. Demultiplexer at the transmitter and multiplexer at the receiver will provide timing synchronization. Okay, synchronous carriers will provide you the frequency or phase synchronization. Thereby you can say that this is a coherent version of QPSK. So thus our coherent detection will reduce the probability of error. It will reduce the probability of error. Now, so what are the advantages and disadvantages? Let us go through the advantages and disadvantages of QPSK. So here the bandwidth usage. So what is the bandwidth of QPSK? It is FB. So how much, if you compare it with BPSK, FB is almost all half to that of 2FB. So bandwidth usage of QPSK system is reduced to half compared to BPSK. That is the advantage of QPSK. Next, the information, sorry, that here you can eliminate this. The information transmission rate, the transmission rate you can say directly of quadrature phase shift keying is higher over BPSK as it transmits 2 bits per carrier. Okay, 2 bits per symbol. Please wait here. So what are the advantages here? You can say the information or transmission rate of QPSK is higher over BPSK because it transmits 2 bits per symbol. Okay, so in BPSK we will transmit only 1 bit per symbol, but here you are grouping 2 bits. So that's why the information rate is higher than BPSK. So third point is similar to BPSK, here QPSK is also susceptible to noise, less susceptible to noise because it has no amplitude variations, because in QPSK we will have only phase variations. So QPSK signal is highly noise immune. That is the third point. Now what about the Euclidean distance? This Euclidean distance is similar to BPSK. So that's why similar to BPSK, QPSK also gives you less probability of error. Okay. Now similar to BPSK, QPSK system also offers high power efficiency. This leads to high SNR for QPSK system. So because its probability of error and the signal power is probability of error is less and signal power is high. So that's why here also SNR is high. This is similar to BPSK, but compared to BPSK, it has two advantages. That is, bandwidth is reduced to half and information rate is doubled. Information rate is doubled and bandwidth is reduced to half. Okay. And a few drawbacks. So this drawback is almost similar to BPSK. Here design of coherent version is complex. So that's why you can add the differential QPSK. You can add a differential encoder prior to the system at transmitter and a differential decoder at the after completion of this general QPSK receiver. You can add a differential decoder at the output section, and at the input section you can add differential encoder. So the differential technique, QPSK technique, can overcome the drawback of coherent version of QPSK transmitter and receiver sections. Okay, so another drawback of coherent version of QPSK is similar to BPSK. That is, it cannot detect the polarity. It has polarity problem. Okay, because whatever drawbacks we have for BPSK, almost all similar drawbacks you will have for QPSK. So to overcome the two drawbacks, you can use a differential encoder at the transmitter section and differential decoder at the receiver section. So that's why differential QPSK you can use to overcome the complexity problem and polarity problem. What is polarity problem? Here you are raising the magnitude by 4, so that once again you cannot distinguish the magnitude as plus or minus 1, because once you take power 4, it will be only plus 1. So output will be always positive. So our QPSK system, similar to BPSK, it cannot distinguish the polarity of receiver signal. So the remedy for the two said drawbacks is to utilize the differential QPSK system. Okay. Now please go through the applications of QPSK. Almost all it has similar applications as that of BPSK. But other than that, please observe the first point here. Please observe first point in applications. Here, in the case of QPSK, the difference between any two constellation point is 90 degrees maximum. Because what is the phase shift between any two successive symbols? The phase shift between any two successive symbols is 2 pi by m actually. Here m is 4. So pi by 2 is the phase shift between any two successive symbols of QPSK. So because of this type of pi by 2 phase difference between any two successive symbols, this type of modulation will have so many benefits because it is high. It's it's flexible. It will be flexible to adapt to any kind of applications. Okay, that is the advantage of QPSK. Next, similar to BPSK, QPSK is it's used in various cellular wireless standards, such as a global system for mobile communication. Generally, this GSM standard it's used in 2G mobile communications, and CDMA, that is code division multiple accessing. Okay, which is a multiple accessing technique used in 3G, 4G and 5G applications. Okay, and similarly LTE, this is used in 4G application, long-term evaluation, and all these IEEE standards, 802.11, and similarly that's wireless LAN, and IEEE worldwide interoperability for microwave access. Okay, WiMAX. Okay, generally we'll call it as WiMAX. That is the IEEE standard used for mobile communication. Okay, next satellite and cable TV applications. So in varieties of these kinds of applications, QPSK signal is used. And similarly optical, these are all the rest are used in, you can use BPSK signal also, but QPSK has much flexibility and you can reduce the bandwidth because its bandwidth is FB, and information rate is higher because you can group 2 bits. Now Here you grouped only 2 bits. For example, if you group 3 bits, what will happen? You can still, it will affect the bandwidth. Similarly, if you increase the grouping of bits, that kind of technique is called as M-array PSK. So what are the other applications? Biometric systems, radio frequency ID tags, multi-channel wavelength division multiplexing. This wavelength division multiplexing is one of the type of analog modulation technique only. Okay, so similar to FDM, this is also one kind of analog multiplexing technique. Like wavelength division multiplexing and frequency division multiplexing are generally used in the analog modulation techniques. Okay, so Bluetooth communication. So in all, these are all the applications of QPSK. And later our researchers, what they did, instead of grouping 2 bits, they have tried to group 3 bits, 4 bits, 5 bits, up to so on, n number of bits. So if you group 3 bits, it is called as 2 power 3 PSK, that is 8 array PSK. For example, if you group like 4 bits, so 2 power 4 will be 16. So that is called as 16 array PSK. So similarly, if you group n number of bits, that is defined as 2 power n array PSK. That is called as M array PSK system that we can discuss in the next class. So if you use that kind of techniques, that M-array transmission techniques, you can reduce the bandwidth and you can improve the information rate or transmission rate. Okay, that part we can discuss in the next class. So any doubts in the today's class? Any doubts? Okay, this is all about QPSK technique. So any doubts? So today I will post this QPSK and yesterday's class, that is FSK, in your WhatsApp group, and you go through that. And tomorrow we can continue with the M-array PSK technique. So any doubts? Please respond.